Good. Any questions about stuff that Jason went over with you, or should we just pick up where he left off? So polar coordinates. So according to him, you all got through like where you're finding the slope of a tangent line in polar curves, but hopefully you graphed a few curves, kind of talked about how polar coordinates and rectangular coordinates are related to one another. One thing I really want to make sure, because it's going to be crucial for where we go from here, is so how do we relate Cartesian coordinates? So let me just share the slideshow. How do we relate rectangular or Cartesian coordinates to polar coordinates? So let's just kind of check in about something basic or something kind of fundamental to polar coordinates here. What do the r and the theta represent? So the what? The radius? What do you mean by radius? Right, so how far out from the origin or the pole? Basically, how far out from, what we think of as 0, 0. Did he talk about how to relate these things together? So can I represent x in terms of polar coordinates? Can I represent y in terms of k? So he might have built it up differently, but let's say this. If I wanted to talk about the sine of that angle theta, what is the sine of that angle? So knowing that this point right here has coordinates x, y, y over r, and the cosine of that angle should be x over r. So I'm hoping or guessing you've seen this, right? Y is equal to r sine theta, and x is equal to r cosine theta. Seems familiar? Cool. Another big relationship that's probably worthwhile to you. So what if we wanted to relate all three of the sides of this triangle together? So how long is this base? How tall is this triangle? So those should be x and y respectively, right? So how do I unite x, y, and r? Right, so Pythagorean theorem applies, x squared plus y squared equal to r squared. But these three are going to be very, very important to you in terms of like migrating back and forth between, am I talking about rectangular coordinates, polar coordinates? Really, those things are different manifestations of the same thing. If I'm going to try to tell you where a point is, now we have multiple ways to do it. And it's worthwhile to know how to go back and forth between those two things. So, familiar from last time, hopefully? Okay, good. So this is going to be very important for what we're going to do now, and that's going to be basically, just like we did with parametric curves, introducing calculus into what we're talking about with polar curves. So I'm giving you a polar curve here, r equals 1 plus sine theta. I would like to find the slope of the tangent line at, under a specific condition. So I want to find the slope of a tangent line. How do I do that? What gives me that information? So I heard two things. I heard the derivative. I'm also hearing Bella. What was that? Okay. So where does the slope appear here? Right. And one thing I want to point out is, like, I'm hearing the derivative. We can't really say the derivative anymore because, just ever since we started talking about parametric curves, there are many kinds of derivatives. So what specific derivative is it? It's specifically dy dx. So if I'm talking about slope, one of the catchphrases you probably remember about slope is this idea of rise over run. So basically, what is the change in y with respect to changes in x? So even though we're dealing with this thing in polar coordinates, in polar variables, we still want to find this variable dy dx. So that right there is our goal. So we kind of have to build that up because we're not dealing with y and x directly. What do we know about y in terms of polar coordinates? So we know that y is equal to r sine theta. And we know that x is equal to r cosine theta, right? So here's what I would like to do. I would like to, the way we're going to get to this dy dx is we have to go through basically our representation of polar coordinates. So now I would like to take a derivative of r sine theta with respect to something over the derivative of r cosine theta with respect to something. So if I take a derivative of r sine theta or r cosine theta, what variable should I be dealing with? Theta. Theta is the input variable. So essentially what I'm doing is taking the derivative of r sine theta with respect to theta and the derivative of r cosine theta with respect to theta. So I'll go ahead and pause there before we actually start computing, but I want to make sure we're okay with the setup here, with why we're building it this way. All right. So now let's just handle this one derivative at a time. In the numerator, I want to take the derivative of r sine theta with respect to theta. How do I do that? Why is the product rule something you have to do? So r and sine theta we can treat as two different functions. For now, let's build this up generally. So basically, I'm going to leave off the one. I'm going to leave the 1 plus sine theta out of it. Let's just build this up, for some generic r. R cosine theta plus r prime sine theta. I'm going to replace r prime with dr d theta sine theta. Does that make sense for that derivative of the numerator? What then should the denominator look like?
R sine theta plus no theta cosine theta.
How are we doing with that? Okay, so this right here, this is generally true for any curve written in polar form. So this will give you that slope of the tangent line. Now that we've done this, can we start evaluating it for the curve we care about? So I got r and dr d theta. What do I swap in for the r's? So 1 plus sine theta cosine theta plus, what is dr d theta? Why? Right, so this is right, taking the derivative of r with respect to theta gives me this. And then I can make the same substitution in the numerator or denominator. So negative 1 plus sine theta plus cosine theta. For dr theta. So if r is equal to 1 plus sine theta, so fundamentally, what does that symbol mean? The one that I just wrote down. The derivative of what? The derivative of r with respect to what other variable? Right. So I'm gonna take the derivative of 1 plus sine theta, treating theta as the variable. So 1 vanishes because it's constant. Yep. So that is exactly where that comes from. So yeah, something to note here is that you might be suspecting that any derivative, so when you take dy dx using polar curves, the derivatives are going to, there's going to be a lot involved. And maybe those individual operations are not terribly complicated, but there's a lot of them. So be careful to keep track of all those moving parts. So we have the derivative. Any questions about how we computed it? All right, what have I asked for beyond that? So let me try to buy back some space. So I want to find dy dx when theta is equal to pi over 3. So I should get 1 plus, what is the sine of pi over 3? It is one of those two. It's important to know which one. It's root 3 over 2, right? Cosine of pi over 3 is a half. Plus 1/2 times radical 3 over 2. How we doing? Oh, so you did this one last time? Okay, cool. So any questions on what we wound up with there? Would you be terribly offended if I left this simplifying to you? So I did not realize that Jason got into this a little bit with you last time. So you have seen this then? Okay. If that's right. So is that okay? Right. So I have not defined it that way, but what is R really? R is a function of theta. But yes, either way you'd like to say it. If you want to drop in f of theta for R or f prime of theta for dr d theta, that's fine too. So yeah, all those notations kind of mean the same thing. So I think we've handled this first bullet. We figured out what dy dx is when theta equals pi over 3. So this next question is something I know we've done something similar to. But now I want to think about this. Where is the tangent going to be horizontal? Very close. So yeah, I need to, when I'm talking about derivative, I need to talk about two variables kind of changing together. So I want dy dx to be equal to 0. Or there's kind of an equivalent condition we can look for. What we really found in this numerator was dy d theta, right? So depending on how you want to look at it, either one of these is going to give you that condition, or we're going to give you a horizontal tangent line, where dy dx is equal to 0 or dy d theta is equal to 0. So what was our d theta in this case? One plus sine theta cosine theta. One more time, Clement.
Plus cosine.
Okay. Can I find out where this is equal to 0? So probably have to do some simplifying. So I got cosine theta plus sine theta cosine theta plus cosine theta sine theta equals 0. So 2 sine theta cosine theta plus cosine theta equals 0. Is that an equation we can solve? I think it needs some more manipulation. I think we can. Any ideas on how we can factor out a cosine? And that leaves us what? Two sine of theta plus 1 equals 0. So basically we can break these apart into two equations. Cosine theta equals 0. Let's just deal with that one first. Where is the cosine equal to 0? Right, so on the y-axis. And where is 2 sine of theta plus 1 equals 0? Or where is sine theta equal to negative 1/2? We okay with that? I'm gonna reframe these into positive. 7 pi over 6, 11 pi over 6. One thing I want to ask now are, we have 4 different values for theta, right? Are all of these places going to give us horizontal tangent lines? Can we be sure of that right now, or are we going to do something a little different? So we said that we get horizontal tangent lines where dy dx is equal to 0, or dy d theta equals 0, right? I think there's something else we have to watch out for. So similar to the pitfall we talked about with parametric curves, it's not really enough to make sure that dy dt or dy d theta equals 0. Something else we have to look at, right? We also have to make sure that the dx d theta is not 0.
That was the one question, but I don't remember, is it gonna last for any more?
Yeah,
Yeah, please would be like that.
you should, yeah. It's not like a huge deal if you didn't, but
Cause I just noticed that I got 2 points.
Yeah.
And I was like, oh, I don't know which one it is, so I wrote both down. Cause I didn't
Yeah.
get that.
I don't remember if they both. Yeah, I need to look at it. I
It was
don't.
like you get like 2 points or something, and then I didn't test to see if the denominator.
I don't remember if they're both valid, but
Okay.
yeah, I'll take a look. So now we can check that. So it's long since been erased. What is dx d theta for us? Someone wrote it down, so I'm gonna give it to me now. No?
The negative sine theta times sine theta plus.
So negative 1 plus sine theta plus cosine squared theta, essentially. Okay. So what do I need to make sure of here? Right. So is that going to be an issue for any of these? What is the sine of pi over 2? 1, right? So I don't think sine of pi over 2 is going to be an issue. How about sine of 3 pi/2? Oh, so let's look at that one. So dx d theta when theta equals 3 pi/2. So that's going to be equal to -1 -1 times -1 plus 0 squared. So that comes up to 0, right? So what does that tell us about that angle we found 3 pi/2? It's, yeah, we're gonna have to distance it. So I will leave it to you to try these last two angles. But just keep in mind that that is something we have to watch out for. It is absolutely possible for, even though you think you have a horizontal tangent line because dy d theta is equal to 0, you might have that issue where the derivative is not defined well. Questions here? All right. So got a new polar curve. I want to find the equation of the tangent line. So tell me how to start that. How do you find your slope? Slope is going to come from dy dx, specifically at this point or at this theta value. How do I find dy dx? Oh, sorry, what was that? Okay. And we can kind of fast forward a little bit. So if I use the product rule on this, I get what? Dr d theta. Sine theta plus r cosine theta. I don't think this is exactly the way I wrote it down last time, is it? Should be identical or should be equivalent though. How are we doing so far? Yeah, so the one thing I want to, I want to make sure that bottom line, yes, this is going to be the way we find this derivative dy dx for any polar curve. Let's remind ourselves, where does this dd theta of r sine theta, where does that come from? Why is that what that numerator looks like?
It's dy dx.
It's not, that in itself is not dy dx. The numerator is not dy dx, it's something closely related to it. It's dy d theta, right? Where does the y show up in there? Yeah, so that's one thing that is the reason why this always begins this way. If I want to find dy dx, what I'm really finding is dd theta, so basically the derivative of r sine theta with respect to theta over the derivative of r cosine theta with respect to theta. So yeah, not a coincidence, and that's always how we begin. That is basically, that comes from the definition of, or the how y and x are represented in polar form. So now that we have like kind of like this skeleton, this template for a derivative, where can we go from here? Okay. We can do r and dr d theta. What is dr d theta for us? So 8 cosine theta sine theta. And our R is 3 plus 8 sine theta. Cosine theta. We said the RD theta was 8 cosine theta. Cosine theta. All right, so I just wrote a bunch of stuff down. I believe is what you gave me. Want to make sure that we're okay with it though. The sine theta, good question. Where did the sine theta go? 8 cos theta, cos theta. You talking about the very first term here?
Yeah, where did this?
The second.
So that's, I think the way I wrote this written down might be reversed from the last slide. So my first term here is the derivative.
Yeah, we found the derivative to be 8 cos theta sine theta.
I think it's just 8 cosine theta. Right, or, yeah, it should just be 8 cosine theta.
Oh, you wrote down 8 cos theta sine theta. Didn't you? Oh, no, because you
So,
started doing that, never mind.
okay, so the derivative, so let's be very explicit here. From the R we have, then dr d theta is what? 8 cosine theta. So that's what all these are.
For the second term, yeah, it's R sine theta. And you have your R 3 plus 8 sine theta, but then you have cosine theta instead of sine theta. For the denominator, bottom one.
Oh, okay, thank you. Yep, that's a miss. You are not. Does it look better now? Okay. Sebastian, was that your? Okay. All right, I think it's all repaired. Now what do we do with it? Evaluate. Let's do this. Let's make a note off to the side here. Since we needed a lot, what is the cosine of pi over 6? What is the sine of pi over 6? Oh, they're 1/2 and radical 3 over 2, but which is which? Yep. Okay, so now we can start filling in. So 8 times radical 3 over 2 times 1/2. Right, this is gonna, so we want to find the equation of a tangent line, right? If I can do anything to help simplify the slope part of this, well. Hopefully nicer than this though. So this comes out to be 2 radical 3. Six minus 7/2? Where'd the negative come from? Oh yeah, you're right, thank you. So yeah, 6 minus. I'm gonna multiply numerator and denominator by 2. So 4 radical 3 plus 7 radical 3 over 12 minus 7. All right, I think that's our slope. That was a long way to get there. Let's do this. I think we're very used to dealing with equations of lines that look like this: y equals mx plus b. Can we go point slope form instead? So we have the slope. Now we need an x1 and a y1, right? So we have the slope of the tangent line, but I don't think we yet know where it is. So how can we find the x and y, the xy coordinate that goes with this slope? What is r sine theta going to give me? Right. So if I want to find y at theta equals pi over 6, that'll be equal to r 3 plus 8 sine theta times sine of theta. I'm just going to drop into pi over 6 already. What does that come out to be? 3 plus 7/2. And what is the x? Seven radical 3/2. Okay, so got my slope first. Now we got a y value and an x value for a point that goes with it. So can we write down our final equation now? Y minus 7/2 equals m, which was 11 radical 3/5 times x minus 7 radical 3/2.
How are we doing?
Any questions? Okay, let's go ahead and move on. Oh, we're done. So, yeah, that was all of 9.3. So yeah, Jason on Friday did most of that with you. So one section left for the semester. So just did a little bit of differential calculus with polar curves. Now we're going to do some integration with it. So let's kind of build this up on things we've done a lot of already. So how do we do areas in Cartesian coordinates? So let's say I have a curve like this, and I want to find the area under this curve between x equals -2 and x equals +2. So if you think back to the tail end of Calc 1, how do we build up areas like this? Like like kind of your first foray into this, where you're talking about area under a curve. How did you talk about it? How did you represent it? What was that back?
The integral of the line from -2.
Oh, that was the first thing we did.
Right.
This was like, I'm thinking like, you probably thought about areas before you talked about integration. Let's find the bounds. So we got the bounds, right? -2 and 2. But before you talk about this area being under a smooth curve, you probably talk about simpler areas first, right? Probably talk about Riemann sums first, right? So that was kind of like your first resort here. I don't have a geometric formula for the area of whatever the shape is, but I do know how to find the area of rectangles. So I'm gonna split this thing up into a bunch of rectangles and find those areas. How do you find the area of a rectangle? Base times height. What are the bases in all these rectangles? Dx, or I'm gonna say delta x because probably talked about delta x being like a finite measurable thing first. What's the height of all those rectangles? It's whatever the y value that goes with it, right? So you probably talked about like f of xi star, where basically for every one of these intervals, I'm going to sample a height. And I'm going to get a rectangle from each one of those things. So the way we're going to find the area in polar coordinates is not, you know, it shares similarities with this. We're not going to be building rectangles, but we're going to be building fundamental shapes that we can find areas of. So here's my polar coordinate system. Let's say I have a curve that looks like this. So I don't know how to find the area of whatever that strange shape I made is, but what we're going to do is this. What are the variables I use in polar coordinates? They're not x and y, but they're what? They're r and theta, right? So I want r to change by a little bit. Well, I want to let theta change by a little bit, and that'll let me gauge changes in r. So let's actually make theta, the change in theta pretty big so we can kind of see what we're doing. Let's say that theta is going to be between, you know, here and here. So if I let this be a small interval for theta, and I basically, these are my bounds now, my theta bounds. When I connect these 2 points, how should I connect them? What shape should that be? It's not going to be a triangle because I'm not going to go straight across, right? Because let's think about it this way. Oh, let's go back. Let's keep thinking about it. In polar coordinates, when theta changes, like, so basically if I sweep out an angle, what happens to r? Does it sweep in like a straight line? It makes like it makes part of a circle, right? So I'm going to make a shape like this, right? So yes, the boundary, like the outer edge of this, is a circular arc. These bounds, these theta values, these are straight lines with the outer edge there. That's a circular arc. I want to find the area of this thing. Do we know what this kind of shape is called? It is wedge. There's a technical mathematical term for it. Called sector. What is a sector though, really? It is it's a slice of pie, metaphorically speaking. It is like Caleb's words where it's a piece of a circle. It is like a sector is this area that's bound by like the center of a circle and its circumference. Doesn't have to be the whole circle, but this is how we find it. So I would like to figure out how to find the area of this shape, this area of a sector. How do we find areas of things like this? Well, let's build it up. You yourself said that it's a circle, right? It's a piece of a circle. So what is the area of a circle? That's pi r squared, right? But what if I don't want to find the area of the entire circle? What if I want to find the area of only a segment of it? Let's say that, let me take some of my shading away. This right here is theta. I would like to find the area of this theta-sized wedge of a circle. And I can rely on the fact that I know how to find the area of the entire circle. Over theta? Let's talk about that. So we're going to exclusively deal in radians. So this theta over 2 pi, what does that represent? That's basically, that is a proportion of a circle, right? Because if it was a full circle, what would theta be? 2 pi. So I want to look at this as a proportion of a circle. So that's where this comes from. Theta, so this area is pi r squared times this like proportion. Theta over 2 pi. We're building that up, yeah. First, I'd like to simplify this thing a little bit, right? This comes out to be what? 1/2 r squared theta. So this is how you find the area of a sector. So basically, we're going to use that to kind of like found our I'm bad at rectangles, I'm even worse at these. Bear with me. But basically what I'm doing here is this. I'm taking this curve and I can't, I don't have a nice geometric formula for whatever these, this area is called, but what I can do is I can set up this. Basically what I'm doing here is I'm adapting the Riemann sum that we've used for, lots of things by now, but now I'm adapting it for use with this thing that is inherently circular. So how do I find these areas? I'm going to bound it between, theta naught and theta 1. And what's the thing that I'm actually integrating? 1/2 r squared d theta. So basically adapting Riemann sum, which was first developed on rectangles, to work for not rectangular areas, but circular areas. How we doing? Thoughts, questions? Okay. So let's use one. I want to find the area enclosed by one loop of this curve, which I think you graphed this exact curve with Jason on Friday. We just want to find the area of a single loop of it. So I'll remind you, since this is our first time out, I want to find the area by the integral from whatever my theta bounds are of 1/2 r squared d theta. So I need a lot of information to set this up. What information do I already know that I need? What's that? I already have r. So I'm going to integrate 1/2 cosine squared 2 theta d theta. Do I know my bounds? How do you know 0 to 2 pi? Are you sure? So if you have from Friday, in your notes, you have a graph of this, right? Let's pretend we don't have that, because I don't have that. I wasn't here. One thing I don't know if Jason talked to you about is polar curves can only intersect themselves at the pole. So if I'm looking for where this thing makes a loop, one thing I can do is this. I can figure out where it returns to the pole, where it returns to the origin. Is this an equation I can solve? Where does the cosine of an angle equal 0? Not 0 in pi. Right, so one thing I do know is that I write down a few angles where this happens, should be odd multiples of pi, right? Pi, 3 pi. We're looking for a balance of one loop, so it was the same number. Pi and 3 pi. So basically any any balance will do as long as I enclose one loop. If 2 theta equals pi and 3 pi, then what's a good set of bounds for theta? Pi over 2 and 3 pi over 2. Questions there? I'm sensing doubt.
Plug pi over 2, with 2 cosine. 2 theta. It doesn't equal 0. It's thrown off by that. Or like how these three relate to each other.
So cosine 2 theta equals 0, so. Wait, sorry, what you plugged in, so you plugged in pi over 2 for theta, right?
Yeah.
Where?
Into the original one.
So cosine of 2 pi over 2 is cosine pi, right? Okay, so I don't believe our equation, so let's go back to the drawing board. Where does cosine of 2, where's the cosine equal to 0? We said pi and 3 pi, but that's not right. What should we have said? Pi over 2 and 3 pi over 2. And that should give us pi over 4 and 3 pi over 4, right? So let's double check again. Does that make sense? Should, right? 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. So from there, I think we have this integral. The integral from pi over 4 to 3 pi over 4 of cosine squared 2 theta d theta. How we doing? So I believe strongly that this is a good setup for that integral, right? Sebastian. Know where we're supposed to, let him say. Questions, go ahead.
The truth is it's full by one loop, so I would should have to do and get half the loop. Some is
I don't believe so. You wanted to look at it?
I mean, if you have cosine data, I would start at pi over 2, you have 3 pi. I just like a circle here. That's actually.
Are you sure this is a circle though?
No, I know, well, if it's a circle with different area, it's not like you do this.
No, I don't think it's I'm not sure it's a circle at all. Are you sure it's a circle? So we only got a minute left. Let's do this. Let's
I don't think we actually grab this.
Let's leave the setup of the integral. Well, you do have one. What do we say it was cosine 2 theta?
It's cosine.
Okay, so it's this rose. So do I know this well enough to figure out what what did we say our bounds were? Okay, I feel good about that. So, yeah, so that's one thing I want to point out is that, yes, these polar curves are based on circles, but yeah, a lot of these equations don't give you circles. And I think I want to point out that just a few minutes ago, when I said what is one loop of this, more than one of you mentioned that, 0 and 2 pi are bounds. Because we're used to dealing with circles, and that's one full sweep of a circle. But yeah, let's dig a little deeper, make sure you actually know what the curves are going to look like. So we set up the integral, we'll compute it next time. But we'll leave the setup for now. I got 11 o'clock, so we'll stop it there. What's that?
But I don't think he posted it.
Yeah, so someone pointed out to me. I opened it and forgot to assign it to anybody.